Hi everyone, my name is Haoran Yang, a PhD student at the University of Technology Sydney. I'm the first author of the accepted paper Meta-Path Contrastive Learning for Multi-Behavior Recommendation. Now, I will present this work to you. With the rapid development of e-commerce, online shopping is becoming more and more popular. Plenty of fruitful logs about user behaviors are generated and are stored on e-commerce platforms. It's critical to utilize this data to improve recommendation systems. However, many traditional recommendation systems pay more attention to purchasing, ignoring other behaviors. Thanks to the development of multi-behavior recommendation techniques, researchers have proposed many models to utilize different users' behaviors. At the beginning, I will introduce some challenges in recent works regarding multi-behavior recommendations. Many recent works notice the limitations of traditional recommendation systems. They try to narrow multi-behavior information to polish recommendation quality. I will introduce you some categories of recommendation models from different perspectives. The first one is utilizing Meta-Path for user behavior modeling, but there are various Meta-Path schemas existing in the heterogeneous graph. Researchers usually take an exhaustion method to find out the base schema. Another type is multitask learning-based multi-behavior recommendation models. They introduce more supervision signals from training set to improve models, but still fail to capture complex dependencies among different behaviors. For example, NMTR assumes that different behaviors are cascading, and EHCF gives a simple transferring schema among different behaviors in the embedding space. However, in real-world scenario, one behavior may not have such a strong connection with its present behavior. For example, in their assumption, users must add the product to cart before purchasing, but in some cases, users would directly buy something without putting into the cart. Our motivation aims to address previously mentioned challenges. First, we need to extract meta-paths from graphs. Under the scenario of multi-behavior recommendation, there are dependencies among behaviors. We also have to find a way to combine meta-paths. We propose the concept of hyper-meta-paths to solve it. Moreover, hyper-meta-paths can be regarded as a method to enrich graph structures like multi-hop, subgraph extraction, and hypergraph construction. Then, to demonstrate the complex semantic information carried by different combinations of behaviors, we choose graph contrastive learning to contrast user behaviors regarding to different products to obtain behavior patterns embeddings of the user. We try to model behavior patterns consists of multiple behaviors instead of independent behaviors themselves. For example, let's assume a user has directly purchased a pen and have viewed carefully before purchasing a smartphone. We can construct two hypermetapaths to describe the behaviors a user takes regarding to different products. We are contrasting these two hypermetapaths. We can know the behavior pattern of the user, that is, what products the user will pay more attention to before purchasing. Next, I will give you some details about hypermeta graph and the proposed framework. Hypermeta graph is inspired by the concept of hyperage to address the limitations of metapaths. A hypermetapath is a logical composition of multiple metapath schemas connecting two end nodes in a heterogeneous information network. We believe that the conventional metapath is not sufficient to capture the interaction information among metapaths. We give out a toy example in recommendation scenarios to help you better understand the concept of hypermetapath. Let's assume a user has purchased a smartphone and before buying the item, the user had viewed the item twice. If we utilize the metapath to model the user's behaviors, we will have three independent metapaths as shown in the first part of the figure. What we can learn from these three metapaths is that the user have viewed and purchased the item. We have no idea about the user's behavior pattern, which means that we don't know if the user purchased the item first or views the item first. Different users usually have different behavior patterns when facing various products. For instance, a ticket man may take a long time to compare different electronic products before purchasing one, but a non-ticket man may not want to waste a lot of time selecting a smartphone. Thus, it's critical to obtain the user's behavior pattern regarding different products to make a personalized recommendation strategy. If we take the Meta-Path to model the user's behaviors, it will be hard for us to achieve such a goal. But we can solve this difficulty by learning a hyper-Meta-Path. We can build a hyper-Meta-Path based on the previous three Meta-Paths, as shown in the second part of the figure. The hyper-edge links the user and the item. The hyper-edge consists of three behaviors that are connected and sorted according to chronological order. With such a hyper-Meta-Path, we can learn the user's behavior pattern from it, which is that the user carefully viewed the item before purchasing, since we integrate the sequential information of the user's behaviors into the hyper-Meta-Path. This is our proposed framework named HMGCR. There are two main parts in our framework. The first part is graph contrastive learning. We will conduct contrastive learning on the constructed hypermeta graphs, so we can acquire different purchasing patterns of the user facing different products. The second part is to fuse the embeddings obtained in the first part to acquire a unified user behavioral pattern embedding for recommendations. The framework is one of our contributions that we first implement graph contrastive learning for recommendation systems. We also conducted extensive experiments to demonstrate the details about the proposed framework, which will be shown later. To meet the experimental requirements, we select two real-world datasets. The first one is Taobao and the second one is Tmall. Both of them are collected by Alibaba Group. They all contain 4 different types of behaviors of users: page view, favorite, add to cart, and buy. The detailed statistics of datasets are listed in the table. We can see that the scales of both datasets are huge. There are more than 9 million interactions in Taobao and more than 1.6 million interactions in Tmall. We conducted comparison experiments on both datasets. There are 6 selected baselines belong to 3 categories. The first category includes GCN and graph stage, which treat different ages as the same in the graph data. The second category contains GAT and RGCN, which distinguish different ages. The last category includes NMTR and EHCF, which utilize multitask learning to process different user behaviors. According to the results, HMGCR with different graph encoders outperforms all baselines and achieves significant improvement on metric and DCG and have good performances on metric recall, which shows the effectiveness of the proposed framework. Moreover, we conducted extensive experiments to demonstrate the details about the proposed framework. First, we studied the relative significance between contrastive learning task and recommendation task. We utilize a hypermeta parameter beta to control the significance of recommendation tasks. According to the chart, when beta is small, the proposed framework does not work at all. With beta increasing, the performances will increase first and then slightly decrease. This phenomenon is reasonable since the main task of the framework is recommendation. If beta is small, the framework will receive less supervision signal from recommendation tasks, resulting in bad performances. When beta is larger, the framework will receive sufficient supervision signal from recommendation tasks, and some information from contrastive learning achieve good performances. However, with the increasing of beta, the significance of contrastive learning drops, leading the slightly decreasing of the performances of the framework. It also verifies graph contrastive learning is indeed helpful to our framework. Then, we conduct experiments with different graph encoders. Graph encoder is the core part in our proposed framework. Choosing a proper graph encoder for the framework determines if it can achieve good performances. To fully demonstrate the performances of the proposed framework with different graph encoders, we select 3 category GNNs, conventional message passing-based GNNs like SG and GCN, attention mechanism-based GNNs including GAT, and graph topological or geometrical structure-aware GNNs, including TAG and GNN. Extensive experiments are conducted on both datasets with various graph encoders. The results are shown in the table. According to the results, the proposed HMGCR with any graph encoders outperforms all baselines. Specifically, HMGCR with SG or GCN slightly outperforms baselines since conventional message passing-based GNNs are insufficient to capture complex user behavior features from the constructed hypermeta graphs. Despite the user interactions in the hypermeta graphs, there are also chronological dependencies among different user behaviors. With such sophisticated relations in the hypermeta graphs, attention mechanism-based GNNs leverage attention mechanism to learn user behavior embeddings while adaptively distinguishing different relations in the hypermeta graph. However, we replace different types of relations which represent user behaviors with different types of loads in the hypermeta graph. We explicitly add the information of interactions among users and items into a hypermeta graph. It means that the improvement brought by those exit mechanisms, like attention mechanism distinguishing different age, is limited. Note that the hypermeta graphs have a structure which is similar to tree topology. Hence, the hypermeta graphs have not only fruitful semantic information but also excellent structure. HMGCR with graph structure-aware graph encoder leverages the advantages of the hypermeta graphs and achieve the best results in our experiment. To verify improvement is brought by our proposed framework instead of TAG or GNN solely. We conduct supplementary experiments with TAG and GNN. Shown in the second table, it shows that GNN or TAG should cooperate with our proposed framework to achieve better performances on recommendation tasks. Fusion layer is the output layer of the proposed framework. It is used to fuse the user behavior embeddings generated in the graph contrastive learning process. We focus on two categories of fusion layers: linear fusion layer, including mean and sum, and non-linear fusion layer, including MLP and PNLF. The experimental results are shown in the table. According to the results, HMGCR taking mean as the fusion layer achieves the best results, and HMGCR taking sum as the fusion layer has similar results to that with both non-linear fusion layers. Overall, HMGCR with linear fusion layer has better performances in our experiments. We note that there are mapping layers in MLP and PNLF. Those mapping layers in the fusion layer map the user behavior pattern embeddings to another space. In this process, mapping mechanism may disturb the user behavior pattern obtained in the space in which the graph contrastive learning was conducted. Hence, we should take a linear fusion layer to output the unified user behavior pattern embeddings to avoid disturbing caused by conducting fusion in another embedding space. That's all about my presentation. Thanks for your listening.